Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark. We're going to continue our discussion of the dynamics of a rotating polar molecule in an electric field. Okay, so we're just pursuing perturbation theory in the usual form, and we found the zeroth order eigenfunctions. We knew those already. We evaluated the first order energy and found it to be 0. And so now we continue to the next order. So again, what we did in this example so far was determine the zeroth order wave function, the zeroth order energy, and then the first order energy, which is again, it's just a problem of quadrature. So, you know, whatever difficulty you have in doing integrals, the integration is in many respects a mechanical procedure. You can easily find numerical techniques. In many cases, it'll do an integral you don't know how to evaluate. Now, the next step is to get the first order wave function psi1, and that is rather different undertaking. So here is the equation that the equation that defines the first order wave function, and I prefer to write it in this way here. This is the defining equation of psi1, and so you see it satisfies an inhomogeneous linear equation, which depends upon psi naught. Now, important point to note that we're going to go and calculate psi1 for a particular case in a moment, just to show you how that's done. But once you have psi1 in hand, once you have all these things in hand, then let's try to go through this without getting too bogged down in it. This is the second order equation. That is it's the first equation in which E2 appears for the second order energy. And you see there's a second order wave function as well as a first order and a zeroth order wave function. But once again, when we apply the bra psi naught to both sides of this equation, then I hope you can see that this term here and that term cancel. They're the same because of the Hermitian property. We're left with this term. This term vanishes, or let me just say this term is necessarily orthogonal because of the orthogonality of psi naught and psi1. Or if we have E1 equal to 0, then it turns out that this term goes away, and so we're left with an equation where E2, that E2 passes through, psi naught is normalized. Here's the important equation for the second order energy. It's just equal to the matrix element, the potential operating on the first order wave function projected back onto the zeroth order. So this is the second order energy is something that defines a response function. It's generally useful, and that's our target for today. Now, here's how we're going to solve the equation for the first order perturbed function, which we need in order to get the lowest non-vanishing energy. Since we saw that the first order energy vanished, we have to get up to find something interesting. So once again, here's the zeroth order Hamiltonian, the potential, zeroth order energy, and the zeroth order wave function. And we've established that the first order energy also vanishes. So now it's relatively straightforward to write down the equation for psi1 because E0 is 0 then the left-hand side of the equation, just the angular momentum operator applied to psi 1, is this ratio of the strengths of the two interactions, which come from these two terms respectively. And then here you see there's an angle, the cosine of theta, and the normalization 1 over the square root of 4 pi. Well, this means, you see, since the angular momentum operator is spherically symmetric, it's rotationally symmetric, when it operates on psi 1, it returns a particular angle. That means that we should, that means that we should expect the angular behavior of the wave function to be embedded in psi 1. It's only going to be revealed by the angular momentum operator, which is spherically symmetric. It's not going to be imposed by it. And indeed, it turns out that cosine theta is a spherical harmonic with L equal 1. I think you can see that. That's just because a cosine theta is x3 over r, so it satisfies our mnemonic. It's a solution. X3 is a solution of the Laplace equation, as is x3 over r, and it's this L is the polynomial order of that expression that we were looking at earlier in the first part of this lecture. So then, it then follows that the first order wave function is of this form. So you see, in this case, the existence of angular momentum, understanding of angular momentum, enables us to solve the first order equation in a relatively straightforward way. Okay, so we've solved for the first order wave function, and we can now compute the second order energy by this simple formula. And well, okay, so this number, maybe this number doesn't mean anything in and of itself, but let's just ask what it means from the standpoint of classical electrodynamics. As we'll see, this describes a very important quantity, the polarizability of the molecule. So in electrostatics, you learn about the properties of material objects when they're exposed to electric or magnetic fields. And one of the classic problems concerns a conducting sphere of some finite radius, which you put in an electric field, and then that results in the sphere acquiring an electric dipole moment. So there is a redistribution of charges on the sphere, with the positive charges on one side and the negative charges on the other. And this is an empirical law that was understood about the electrical properties of matter in ancient times, before there was any known quantitative theory of how matter responds to electricity. And so it turns out that there's a very useful convention, the relationship of for weak fields is a linear response. So the dipole moment induced by an applied electric field is just proportional to this constant that's characteristic of the object, which for a conducting sphere is just the cube of its radius. And that's when we use the CGS units for the electric field and charges. Now, as it happens, it's easy to show this from the defining relations. The relationship between the polarizability and the second order energy is just given in these simple terms. So this means we can now use quantum mechanics to describe the polarizability of matter. It's really the first, and to date only, fundamental theory that allows us to understand electrical properties from first principles. So when we apply it to this potassium rubidium molecule, we find that the polarizability in the ground state is given by this expression, and this again has the dimensions of volume, so it looks like a conducting sphere that is 25 angstroms, or 2.5 nanometers in radius. I mean, I'm just using this as a measure of the number. Now, I want you to know the following interesting point, interesting to me. The polarizability, which is the ratio of the induced dipole moment to the applied field strength, actually diverges as one goes to the classical limit, taking h bar going to 0. So for a rotating molecule, if we lived in a classical world, the polarizability would be infinite. And that, I think you can see, is because for a rotating molecule with a dipole moment, if there were no energy cost of localization, which is due to the uncertainty principle, then the molecule would just the dipole moment would be localized instantly by even the smallest field. So this shows that, at least as concerns the behavior of a rotating polar molecule, the electrical polarizability of matter is definitely a quantum effect. That is, it exists. It ceases to exist when h bar goes to 0. We're going to see another example of that, actually of a very different type, in the next part of this lecture.